Good afternoon, everyone. Thanks for joining the talk today. Hope everyone got your coffee. My name is Sandeep Umadi, and today I'm presenting with my colleague Eric Shob. We both work at Dropbox, and we are going to talk about storage at Dropbox, especially about our Exabyte-scale object storage system, Magic Pocket. It's a silly name, but a serious system. All right. If you don't know about Dropbox, it's a global collaboration platform. We have over like 700 million plus registered users and over 100 million plus monthly active users. One of our core products is File Sync and Share. Most of you might be familiar with that particular product. Our storage infrastructure basically powers this File Sync and Share. Dropbox users upload over a billion files per day, and this system, Magic Pocket, ensures that every file is safe, secure, and accessible. It's almost like a decade back, the company made a decision to shift from public cloud storage offering to store our user data to build a in-house storage system. That was a monumental decision in terms of like shaping companies' overall like infrastructure. Here is the quick agenda, what we're going to discuss today. I'm going to provide high-level architecture overview about this storage system, kind of like basic building blocks, how they all fit together, and how our IO path works. And after that, I'm going to talk about our SMR adoption and the journey. What are the kind of challenges we faced over the last few years with SMR, and how we address those challenges and so on. And next, I'm going to talk about like some of the operational insights. What is it to manage this system at scale with a small team of engineers, and what are the learnings, and maybe a few of them might be good takeaways for you all. And then Eric is going to talk about hardware evolution and some platform insights about the hardware. And then like we'll conclude with what's next and any Q&A. All right. Yeah, this is like 100,000 foot view. I know most of you probably worked on large-scale storage systems. When we are going through this architecture, you might see like a lot of similarities in our system with various published systems out there. There are also like a few very intentional and conscious design decisions our founding engineers made. Most of them have like bias for simplicity. So I'm going to highlight how those are helping and then how those are scaling over the last decade. So at super high level, it's a geo-replicated key value storage system. So every byte gets uploaded into Dropbox. It automatically gets geo-replicated so that we can tolerate for our users any one single metro going down. And it provides 4 nines of availability and 11 plus 9s of durability. And then we have ingress and egress rates around like tens of terabits per second in our system. It's very much built for our FSS workloads. It's not like super generic public cloud storage system. It's very much optimized for Dropbox users and then to store our user workloads. However, we also use it for some of the internal workloads like logs from the various services running internally in Dropbox and also like search index and stuff like that. But that percentage of the data is like very small. Most of the data in our system is dominated by the user data. It's like almost 99% of the data is user data. The system has very simple and very basic APIs, unlike public cloud storage offerings where you get like extensive APIs. All we do is like we provide these 3 or 4, put, get, and delete. Put takes a key, and then it takes a payload and MD5. Typically, keys for our user data workloads, it's a SHA-256 of a block or a blob. Since it's file sync and share, Dropbox client basically chunks a file from the client devices, like from your laptops and mobile phones and so on, to 4 megabytes, and then it uploads to this backend storage system. And For us, the key is like very opaque. We don't care whatever it is. But for our user workloads, it's a SHA-256. It's a unique value. And MD5 here is like it's similar to any other storage system, right? You want to protect it from over-the-wire corruptions or any in-memory corruptions and so on. So you validate in each your hop that the data is intact. The clients provide a key and then ask for to get the data, and then delete is same. You provide a key and then you issue a delete. Before I dive into our core components and the critical I/O services, a few data types and terminology. The hash is the key, as I mentioned earlier. It's the unique identifier to address a blob or a block. And the blob is like one data value here. The maximum size is the 4 megabytes, as I mentioned earlier. But 4 megabytes is pretty small value in a multi-exabyte system to deal with. So we pack those blobs into append-only fixed size buckets. It's typically like 1 to 3 or 4 gigabytes of size. And volume is a logical representation of this bucket. So volumes are like two types in our system. But they're either like replicated volumes or erasure-coded volumes. We do 4x in initial replication, and then later we erasure code them into either like Reed-Solomon 6.3 or LRC 12.2.2 erasure coding. And the extent is a on-disk data which maps one-to-one with the bucket. So if the bucket is like 2 gigabytes, extent is 2 gigabytes. And these are managed by object storage devices. I'm going to talk more in detail about object storage devices later. So to put everything together, a blob is identified by a key, hash, and it gets returned to append-only buckets. And then the buckets are grouped into volumes and then stored redundantly across multiple machines so that you can tolerate more than like 2 failures. A quick high-level topology. We have Pocket at the highest level. Pocket consists of 2 or more zones because everything is geo-replicated, and then we use the Pocket. For example, for production, there is a production Pocket. For stage and test environments, there is a separate pockets. So think it as a one storage instance, a Magic Pocket instance. And then there is a zone. Zone is the metro. As you've seen earlier, we currently have 3 zones in US West, US East, and US Central. And these are organized into geopairs. A zone contains number of cells. A cell contains number of storage machines, and cell is the scaling unit. So once we get like more capacity and so on, we create new cells. It happens once in a while. And also similarly, when the hardware ages out, we decommission the cells. And cells are like typically around 100 to 120 petabytes. I'll talk about like why that limitation later. So now getting into core components. Front ends, these operate at zone level. So the scope is at the zone level. These are pretty much stateless, horizontally scalable services. We run them in Kubernetes. So during the peak time, there are probably thousands of instances are running per zone. During the non-peak time, we'll scale it down accordingly. This is the only public endpoint. So if any system within Dropbox wants to talk to Magic Pocket, they use their front-end client, and then they talk to the zone. And it handles all the high-level APIs, whatever I described earlier. The next one is the object storage device. The scope is local to a cell, meaning that it doesn't span across multiple cells. In the context of OSD, we have like 2 different terminologies. One is the OSD machine. It's a single storage server, and we typically have our storage servers packed with 100 disks. And then there is a OSD daemon. We run it like 1 per disk. We run everything in our system as a gRPC service. So every disk independently advertises itself as one single instance. Each daemon is a key value store. So it represents the disk and then stores your blocks by the keys. And this is the persistent layer. And OSDs typically operate a lot of operations at the extent level. This is like very critical component, and architecture and then how it kind of works might require its own dedicated talk, like how we maintain metadata and all that stuff. The next service is master. This is like one I wanted to highlight on the simplicity. Again, this is a local to a cell. We run one per cell. It's not in critical IO path. It's kind of like think it as a brains of a cell. So this is responsible for like all cell level control path operations in terms of like health checks, are all our disks online, detecting the failures, and if it detects any failure, initiating repairs for those failures. And let's say when the disks are getting hard swapped, whatever the new disks come up, we wanted to fill them out with redistributing the data in a cell. And similarly, it performs like garbage collection, compactions. It initiates the erasure encoding and everything. It does like a lot of operations. So this is what makes the cell size as a limitation. So it has to keep all the context about like what are the buckets, what are the extents, what are the volumes exist in memory, so that it can iterate on all of them and quickly perform various actions. And here, you might see like some systems kind of like go with, to design this kind of like component, some systems might choose kind of like distributed consensus protocols. You introduce like Raft or Paxos and make it, instead of having singleton, you can kind of distribute the responsibilities among like multiple small services. But we avoided that. We kind of chose with simplicity, went with, instead of kind of like going with the complexity of distributed coordination, we just with a singleton, and which is working well for us. The next one is volume manager. Again, this one is local to a cell. We typically run tens of these things. As I mentioned earlier, master is like more of a control path thing. So it initiates the operation, and somebody needs to carry out those operations, right? So that's done by this volume manager. So this is the one which performs the erasure encoding data, merge repack of volumes, and reconstructing any missing data in the system. And also this is in our critical path. Let's say if you have a data piece which is part of a erasure encoded volume and the disk died and you get a live read request for that, this performs like reconstruction reads and serves it to the clients. The next two are our metadata layers. One is the block index and other one is the replication table. The block index, the scope is at the zone level. So this is where like we maintain, hey, what are all the objects exist in a particular zone? And then it has information about, given a key, where it exists, like which cell and which bucket that particular thing exists. Here is again like one intentional design decision. We did not go with distributed hash table or like a trie or anything like that for our metadata. We just offloaded all that responsibility to just giant sharded MySQL. It's a very big sharded MySQL cluster. So you don't have to re-implement anything. You get all the niceties from MySQL directly. And the other one is replication table, which is scope is like per cell. Every cell has one of these databases. It's much more smaller compared to block index. Block index is having everything, right? So we're talking about like trillions of objects. They're all maintained in the block index. And the replication table contains information about, given a bucket, where this particular block exists in terms of like where is the volume and the volume to actual OSD mapping, so that you can find the routing information very quickly by just querying the MySQL. One last final component is the cross-zone replication. The scope is zone-wide. So this is the service which replicates the blocks from one zone to other zone. And it uses the basic get and put APIs, whatever we provided the zone level. And now putting everything together, here is the quick flow of like how a put block works. So the clients send the put block request to our front ends, and we first check the block index. Remember, this is a key value storage, so it's a giant deduplicated storage system. So if the block already exists, you don't have to upload it. You can short circuit and then say call it done. But there are instances where for the same key, the data might have changed. So the MD5 might be different, or the clients might actually ask to forcefully upload it. So then we kind of like forcefully rewrite that particular entry in the block index. So how does that happen? So let's say if the block doesn't exist, then we need to know where we have to put this particular block, right? We look at these like block index and replication table. They are like MySQL databases. So they're fronted with some stateless services, gRPC services. So all the cells combined together, there's a service which kind of represents all the replication tables. And we look for what are the open volumes where we can actually upload a block into. And our front ends get those open volume information, and it issues a 4x replication right to the OSDs at that point of time. So this like step 2 and 3 are like more of a metadata lookups. And once front ends have that information, we typically do the 4x replication. So we identify one of the OSD as a primary OSD, and other 3 are secondary OSDs. And we relay the write to one OSD that issues parallel write to 3 other OSDs. And once everything gets persisted, it acts back to the front end. And eventually, we act back to client. So one step here is not shown. When we persist this information in the block index, saying that, hey, this is where the now block has been written, we also enqueue into a queue for geo-replication. And think it as like step 7. Asynchronously, there is this XZR, which I described earlier, consuming this queue, and it replicates the block into the other zone at that point of time. So, and if you think about get works like very similar. So you get the get request for a key, you consult the block index to see if this block exists in the system. If it exists, you kind of like know what is the OSD information about this block, looking at the replication table, and you issue the read request to the corresponding OSD and return back it to the client. It's kind of like very identical to this put request path you see. Yeah, so that's at like a high level, everything putting together how the system works. Now let's look into SMR and our adoption and what are the challenges we faced over the last few years. I'm sure most of you are familiar with SMR. So it's a shingled magnetic recording. In the conventional magnetic recording, you have the tracks adjacent to each other. With the shingled magnetic recording, tracks are overlaid, so you cannot do the random writes. You can only perform the sequential writes. It gives the increased density, 20 to 25% compared to CMR. So that means it's a cost effective. When we started to adopt SMR, this was back in 2015. Initially, our services like the data path services, like OSD and volume manager, they were written in Golang. And for OSD, we were actually using Linux file system where all these extents are managed as a large files, 1 or 2 gigabyte files. And we used to use XFS file system for that. But I think the team decided back in the day, if you have to start adapting high density drives, with Go, it has like overhead, right? It has like language, runtime garbage collection overhead. So we wanted to use something like memory efficient. That time, it's a super early beta on Rust actually. Rust was, I think May 15, it was like 1.0. We were adapting around that time. So there were like not a lot of libraries were available, not a lot of open source crates were available. So we had to create so much async framework and all in-house. But at the end of the day, it kind of like worked out really well for us. Adoption of Rust, and then Rust took off really well. It's an awesome community out there. Yeah, so what we did was we used libzbc and then created a custom file system. We didn't want to use Linux file system or the block layer or anything like that. So we use the RAS-SCSI disk, and then we have our own custom file system for that. If you think about it, like our blocks, as I mentioned, the maximum size is like 4 megabytes, but the average size is like somewhere around like 2 megabytes. So if you have 20 terabyte drive, and if the block size is 2 megabytes, you have almost like a billion blobs per machine, right? 100 disks and then 20 terabytes, it's a 2 petabytes capacity, and then you have 2 megabyte this thing. So there is like a lot of metadata we have to maintain. So we use the conventional zone to persist all this block list information on the OSDs. And if you have to read for any lookups and so on all the time to from the disk seek, it will be 2 disk seeks, right? You have to first look at the metadata, and then you have to look at the fetch the actual block. It's going to be like expensive. So we decided to introduce in-memory index. And again, like our keys are a bit long. SHA-256 is 32 bytes, and it can be like any size. It can be like more than 32 bytes as well. So it won't fit. Like you can't, your memory needs become like very expensive. So we have CMPH, if you guys are familiar. It's a C minimal perfect hashing, very compact data structure, which help to kind of like hold all these blocks in memory very easily. And also, when we were starting, we thought probably SMR sequential writes, it's all going to be slow. So let's introduce a SSD cache for live writes so that we can stage into SSD cache first and then later like flush into HDDs. It kind of worked well in the beginning. Later, we had like some challenges I'm going to talk about in the next slide. And also, as I mentioned earlier, the Rust being like super early, whatever the libraries were available were not working out well for us. And we ran into some performance problems and so on. We use gRPC in all our services. So we had to implement our own protobuf serialization and deserialization framework, which has been like open sourced as well. It's called PBJelly. Yeah, so SSD cache bottleneck. So I think this is around like sometime in 2020 or so, we started observing this behavior. So we went from 8 terabyte drives to 14 terabyte drives in our fleet, and then started to increase the disk densities over the period of time. And also, we used to have like less number of HDDs per server, and then we increased that drastically to 100 from like, I think 32 to 100 or something like that. So as you see, these like 2 different y-axes. Over the period of time, the number of servers in our fleet started to go down, even though the aggregated capacity in our fleet was increasing. And now we used to have only like 1 or 2 SSDs per server, which started to become bottleneck. We kind of increased our servers next to 100 gig, and the aggregated throughput of all the disks was like much higher than what a single SSD can handle it. So the SSD started becoming bottleneck. You can solve this in many ways. People can add like more SSDs or introduce an ingestion layer. There are always like trade-offs, right? Cost and complexity and so on. What we decided was we decided to just eliminate this SSD cache completely and try to just write directly to the HDD and then see if we can tolerate the latency and everything. So this is before and after. So the left one you see is with SSD cache. So the way it used to work is the blocks are initially staged into SSD cache, and the metadata also committed to SSD cache. Later, it used to be flushed asynchronously to SMR disk. When we decided to eliminate the SSD cache, we introduced this inline metadata extents. So what we do is we only have very few open extents in any disk. So when we are writing the block, we also write its metadata. And when we close the extent, we kind of like have the in-memory block list information, and then we flush that into conventional zone at that point of time. There are like many scenarios. You can think about it like, okay, what happens if there is a crash when you are doing a middle of writes and things like that. I don't think we have time to go all over those, but we handled all those failure scenarios as well. There were like many wins with this project. one, we were able to delete bunch of code. We didn't want to. We were like provisioning SSDs and had all this like cache code, which was very happy to be get deleted. And one less hardware component. We used to have some failures in our system, like some of these SSDs go bad, and then it takes out entire machine, like in terms of like you cannot like perform any more writes. So that was gone, and then cost savings, right? So one less BOM in the system, so you save money with that. And maybe this counterintuitively, it also improved the performance. As it was bottleneck, we were not getting like a lot of throughput, and the latency was high. So with SSD, as you see, let's say we were getting around 500 puts per second. And when we removed SSD, as we had like more aggregated bandwidth from all disks, it started to go almost like 1500 blocks per second. And the latencies went down. This is the P99 latency. It went down from 1.2 seconds to almost like 200 milliseconds. All right. Yeah, operations and lessons. Little bit background. So the software engineering team is around like 8 to 10 engineers, and we are managing this entire system of multi-exabyte scale system. The team consists of both SVEs and SREs. We interface with many teams. The team is responsible to interface with the hardware team in terms of like bringing up new hardware into the fleet, qualifying, and things like that. And we work with the capacity engineering team, where like new capacity gets landed correctly, ensuring that there is always like enough runways, and we are not like under provisioning or over provisioning our data centers. And we work with the data center operations teams who are managing physical hardware, like replacing the hard disks and repairing the machines and whatnot, and also fleet orchestration and security, and then few other teams. Like you have to frequently upgrade your OS, you have to take enough security measures in your fleet and so on. Yeah, with that, like, what are the lessons operating this thing at scale? The very first thing is verifiers. I described only, let's say, 10 to 20% of the software components in our system. A lot of the services perform like many background operations. A bunch of them are like verifiers. So one important lesson we had was verify every single invariant in your system, right? Let's say if you are doing 4x replication, if every blob of data has to be in 4 places, verify that, and verify that within a period of time. And so, for example, we have consistency checker between like block index and our storage servers. So if your block index, let's say, has like 5 trillion objects, within a week, we have this SLA internally. Within a week, we wanted to go through all the objects in the block index and then verify that they are still there in the storage servers. And there is also consistency checker between our file system. So Dropbox, when the users are uploading, there is actually file system up above the stack of Magic Pocket. So that has all this block list information. Given a file, what are the blocks exist? And though we need to have a consistency checker between that and then the MP's block index. And there are like many more verifiers like that we have. And these verifiers, we wanted to make sure that there are always 0 violations in the system, right? If there are violations, you get paged, and engineers don't like to get paged in the middle of the night. So we ensure that there is always good consistency exists around. Now if you want to always have 0 violations, how do you ensure that your verifiers are actually working, right? You need to know that your verifiers are actually working. So this is what dovetails like nicely into DRTs. So we perform disaster recovery testing frequently, and the DRTs serve 2 purposes for us. One, if your system is designed to be fault tolerant, exercise that regularly so that it actually really fault tolerant. And the 2 is, if you have all these like various verifiers, perform some DRTs so that you are verifying the correctness also periodically, so that there are no bugs are happening in the system and so on. To give you a couple of examples of the DRTs we run almost every day, is like one is a zone failover. Since it's a geo-replicated storage system, we wanted to make sure that even during the peak hours, we can take down one zone completely offline for 30 minutes or so, and then ensure that there is like no availability impact for our clients. So this happens like weekly once, and it's all automated. It's always happening. And similarly, as I mentioned, like there is a consistency checker between block index and the storage servers. We run a DRT where we kind of like insert a invalid entry into our block index, and then we let our consistency checker find that violation and then report the violation, so that that way we know that there is like no bugs or regression in the system. The next aspect is SEVs and blameless postmortems. Always declare SEVs quickly in terms of availability and durability impact, and then perform the blameless postmortem so that you are making your system more anti-fragile. You're fixing in a right way. And maintain strict SLAs with the dependency teams. Like for example, when we are doing new hardware qualifications and so on, we have SLA with hardware team where per terabyte they need to provide like some amount of repair throughput and things like that. So having those in place helps easily teams to iterate like fast. And similarly with our capacity planning team, we have a replication overhead SLA. So we have to always meet that SLA so that capacity is planning correctly, like how much supply we need to accommodate the demand. And always have like good hardware diversity, multiple drive models or like multiple vendors and so on, so that any sudden massive failure is not causing any reliability risk for your system. And bias for simplicity, anything you're doing, always try to have simplicity in place. Like don't lean towards simplicity in stuff like going to complex decisions. And as Nassim Taleb says, invest in preparedness, not prediction. So always assume that things will go wrong, and then have your tools and then exercise them periodically. So a few things we do is like, we assume that the data losses can happen, and then you need to recover from our other geo-redundant zone. So we have the tools which can quickly recover the data from the other zone and so on. And the last but most important one is like team culture and discipline, right? If you might like build your system like very fault tolerant and so on, but let's say if you don't have the right culture, and then if your engineers are going and then YOLOing in production at the same time everywhere, that's something you cannot like really guarantee. So have a good practices in place and then good culture in place. All right, with that, I'll hand it over to Eric to talk about hardware evolution.
All right. I like to think of Magic Pocket as a co-design between hardware and software. Sandeep covered the software. I'm going to cover the hardware. A little bit about myself. I run the hardware team at Dropbox. Pretty small team. It's a team of 6. 3 of the guys are in charge of all things storage. We have a couple of tiers in Dropbox, hardware tiers. We have a compute tier, database. We have some AI servers, and today we're going to talk about our storage servers. This is actually a top-down picture of our 6th-gen storage server here. The main objective of this talk is just to share the journey, the hardware journey that we've been on. We've been doing hardware for over 10 years. We've been along that ride for a good portion of it, and we've been shipping hard drives in our data centers for over 10 years as well. So hopefully if you're working in a similar space, I can share some learnings and you'll be like, that Eric guy was pretty smart. Maybe I should do that in our company too. All right. This is 10 years of shipping servers in our data centers. I'm actually lying a little bit. There were some previous generations too, but those were kind of in small quantities and things were ad hoc there when we were in our growth stages. We really started forming best practices and shipping things at scale, at the rack level, at generation 1. You fast forward 10 years from now, where we are now, we just released our Gen 7 design. All the guys like to come up with code names, so we used to call things by the wrestlers, and now we switched to cartoons. So when you hear me say Sonic, I'm talking about Gen 7 here. That's our newly released server. a couple of interesting things here is, for the first three generations, maybe four, what you saw when you're designing servers, or if you were trying to just modify an off-the-shelf design from an ODM or an OEM, they really didn't have that many enclosures in the system. So we were hovering around 36, 40, 50 drives in a bathtub design for a while. And then we really started increasing the enclosure count. Right now we're hovering around 100. And there's some trade-offs when you get to that dense of a system. So, one trend here that's driving capacity is enclosure count in a system. I mean, back in Gen 1, we were at 144 terabytes, and Gen 7 is designed to start at 2.7 petabytes. That's what we're shipping now. But we designed that to hit all the SLAs that Sandeep talked about, and we want to scale that all the way to 5 petabytes. So in theory, we should be able to support 5 petabytes at the node level on Sonic. Another thing that's been driving capacity here is just drive density. I think we doubled the drive density over the last 10 years, or last 7 years. And so those two things combined make it really interesting to work on storage at Dropbox. And there's a lot of cool things that you need to solve for when you get to 2.7 petabytes plus. And we'll talk about some of those. So, there's trade-offs when you're designing systems, especially very dense systems. These first two ones are probably the biggest trade-offs I can think of. There's nothing stopping me for putting 200 drives in a system, but guess what? It's going to be really hard to cool those drives in the back. And if I do want to cool them, let's say I want those to be 45 C, which is a good operating temperature for a hard drive, well, I'm going to start having to, spin some fans a little bit faster. And what happens when you spin fans is you create some acoustical noise or vibration. And, it turns out hard drives don't like vibration in the system. A lot of weird things can happen when you introduce a lot of vibe in an enclosure. So, what do you want to do if you want to fight vibration? Well, you want to either get a new fan or a bigger fan, or if you can't do that, you might have to spin your fans a little more slow. But the trade-off there is you're going to be running your hard drives a little bit warmer. So, there's kind of a balancing act to get that right when you're going to 100 or 100 plus. And I'm actually going to give an example of that in the next slide. Another thing that seems obvious is, be aware of your weight and power constraints. In our data centers, we have a 3,000 pound per tile weight limit, and we also have a fixed power limit that we need to be aware of. And, you got to project that out for your design or your architecture. And what I mean, just an example of that, let's say you didn't account for a dual actuator pulling about 3 more watts. Well, you might blow your power limit if you need dual actuator for that design, right? And you might have to redesign some data center stuff that might take a while to do. This last bullet is an ever-evolving thing. It's really, I call it an interop exercise at the firmware level. There's always new HBAs, expander firmwares coming out from our partners. And there's always new fixes for drive firmwares too. And making sure that all plays well with the OS and kernel on top of that is a never-ending exercise that my team does. So these are some of the challenges. Here's an example of a vibration challenge. So, our 7th-gen system, Sonic, is made by 2 manufacturers. We're dual-sourced. And what we did here is we sent both of these platforms to our hard drive vendors, and we asked them to characterize the box. And when I say characterize the box, what does that mean? That means they use surrogates, hard drive surrogates, and other telemetry that might be inside hard drives, and they measure things like acoustical noise and other types of vibration. So they actually put little microphones and other type of sensors in different slots. And then they project out a couple drive capacity points past what they're shipping now. And they come back with a report and they say, hey, that system that you thought was awesome because you designed it, turns out you have some more work to do and it's too noisy. So here's a real example of a system, like look at platform 2, where we have to maybe make some of those trade-offs where we're running hard drives hotter in order to enable these drive capacity points because that platform is too noisy. All right, this is another timeline, another evolution of what we've been shipping at Dropbox. On the bottom here is all the drive models that we've enabled over the past couple of years. The ones in red here, they're no longer around. A little interesting war story here. That first drive that we shipped at Dropbox was a client drive. It was rated for 3 years. We ended up running that thing for about 5 years until the AFR started to explode. And we started looking at it and we said, hey, wait a second, that's a client drive. We better get those guys out of there. But right now we have 7 different hard drive models in the fleet. Since 2018, that 14 terabyte drive right there, that was an SMR drive. And that's what our colleagues and the software guys in Magic Pocket, they helped enable that new recording technique. And there's a couple of other interesting facts here, but one is disk capacity has doubled in around 7 years. And another neat little fact buried in all that text is, power, even though disk capacity has doubled, power has stayed relatively flat. Yeah, so in 2008, we have 7 years of experience running SMR. Sandeep talked about it a little bit, but software is sort of free. So if you have an opportunity to enable SMR and your application allows for it, what do you get from that? You get 10 to 20% extra capacity, right? So that's a big benefit. I just ran the numbers today. We have 98% of the fleet is SMR. We have one drive model that's a non-SMR a capacity point in there. I kind of want to get rid of it so I can say we're 100%, but that's too costly. They won't let me do that. Our first drive was, I think, a 5-platter drive, and the one that we just shipped is 10-platter, and we're looking at 11 platters. So it's really amazing on how many platters they can stuff in a 3.5-inch square. Aerial density has around doubled, and there's new recording technologies coming out. SMR's been around a while. There's always improvements for the reader and writer head, and there's new techniques like heat-assisted magnetic recording that's coming down the pipe as well. So I don't think I have much time here. I'll make this quick. This is a data center top-down view of comparing 4th gen to 7th gen, right? So if we were to ship an exabyte of storage cabinets in a data center, the amount of space we would need is represented for 4th gen would be represented in the blue. Or 7th gen, since we can pack so many more petabytes in a cabinet, we can actually save 75% less space. And that's represented in the green right there. And that's sort of cool, but I think the more interesting thing is to serve an exabyte. If you compare, maybe 5 years ago, you can serve an exabyte with half the amount of power. And that's because the drive vendors are doing a really good job keeping power relatively flat. All right, I'm going to have to breeze through this. On the left here is the life of a byte going through Magic Pocket, hitting the operating system, making its way down to an HBA and an expander ecosystem, and hitting the disk firmware. The picture on the right there, that pie diagram is I went back the last 2 drive quals that we did. I went back and looked at where all the issues were, all the issues that we encountered, and they're all in that blue bucket there. So, and that's been a trend the last maybe 5 years. So we spent a lot of time trying to improve how we test and where we spend our time in that blue bucket. And I'll give an example of what we do. Every vendor that we work with in our designs, an HBA, an expander vendor, the disk vendor, they all have our hardware. So the very first thing that we do when we design a system is we ship them our systems. So the goal there is to have a true apples to apples test environment. And why is that important? Well, what used to happen is we would work with a drive vendor and we'd have an issue. They'd say, hey, go pull a trace. We'd get a trace. We'd provide it to them. They'd have a fix. They'd ask us to go validate that fix, and we'd have maybe 20 emails back and forth. Now the engineer can just walk down the hall, grab a trace on our system, apply the hot fix, verify it, and send it to us without really bothering us that much. And why that's important is we can close the triage, the time to triage and time to deploy. We're a lot faster with our time to deploy now, from the first time we get a sniff sample to when we launch into production. Another thing that we've done very well is we try to hit over 1 million hours for drive testing. We feel that after 100 hours, you really get to know the drive. So we test at scale both on our site and our vendor site as well. And that's been an incremental improvement as well. All right, so what's next? A couple guys have seen this. I'm certain of it in this room. Really, where the focus should be here is on the right. On the right shows these new recording techniques, and then on the y-axis shows the areal density that you get if you can onboard those recording techniques. And then the x-axis is the where we are right now, and you can see that we're straddling ePMR and Hammer. So the focus for a lot of the people, hyperscalers, is enabling that next areal density band, or that new magnetic recording technique called heat assisted. It doesn't, for Dropbox, we're straddling both right now. There's still some legs left in ePMR. I think when, we're seeing 11 platter designs, and we still see incremental improvements for areal density. But a lot of our focus is enabling that Hammer band as well. All right, quick parting thoughts. That's the end of the journey. There's some trade-offs when you're designing big systems. That's thermals and vibration is key. Remember those. If you don't have a tight partnership with your vendors, I'd say there's benefits in doing that if you can afford to do that. And then really we're there's some new technologies coming out for hard drives, and those are really going to change the game for capacity points. We're hoping to see 100 terabyte hard drives in our systems pretty soon. All right, I think I hit my time here, so that's the end of the talk. All right.